Hi guys, Audrey here. So today we're going to start the integration of rational functions. So first we need to ask ourselves, what is a rational function? Well, a rational function is when you have a polynomial on top and a polynomial on the bottom. So this is going to be a polynomial divided by a polynomial. And remember, polynomials have positive whole powers. So like a constant could be considered a polynomial. X to the fifth plus 7x squared is a polynomial. But the square root of x has a fractional power, so that is not a polynomial. 1 over x, that's x to the negative 1, that has a negative power, so that's not a polynomial. Okay, so rational functions are polynomial over polynomial. The first thing that we want to think about when it comes to integrating them is polynomial division. So if what we have is a rational function where the degree of the numerator, so remember the degree of a polynomial is the highest power. So if the degree of the numerator is greater than or equal to the degree of the denominator, then we're going to need to divide. Come on. We've actually already seen a special case when the degree of the numerator is equal to the degree of the denominator. So we're going to separate this into two different cases. Case one is when the degree of the numerator is equal to the degree of the denominator. And in this case, we do what we have learned, that special division. So I'm going to do one problem just to kind of remind you guys of what it is, and then another problem where we see that special division becoming a little bit more challenging now that we know more integrals. So an example of special division would be, let's say that I have x over 8x plus 5 dx. So this is a really straightforward problem. I see that I want to make the numerator look like the denominator. So I'm going to first multiply by 8 on the inside and then divide by 8 on the outside. Note, I cannot factor this 8 from the denominator out because it is not a factor of the denominator. If I pull it out, then I'll have to have x plus 5 over 8 left in the denominator. So I can't just like bring the 8 out like that. So instead, I multiply by 8 and divide by 8. And then I add 5 and I subtract 5. So what I end up with here is 1 over 8, 8x plus 5 over 8x plus 5, minus 5 over 8x plus 5, which results in 1 over 8, 1 minus 5 over 8x plus 5 dx. Now, both of these are known forms. We can easily just take the integral. So I end up with 1 over 8 times x minus 5 over 8 natural log of 8x plus 5. Remember, we divided by that 8 because the derivative of 8x plus 5 is 8. When the derivative is just a constant, we divide by that constant. So here I end up with 18x minus 5 over 64 ln 8x plus 5 in absolute value plus c. Okay, let's now take this special division one step further and see how we can use it in a little bit more complicated questions. Okay, so we have the integral of 4x squared plus 13x plus 12 over 4x squared plus 5x plus 7. In this case, it's really straightforward. The first part, because we have 4x squared on the top and on the bottom. So I don't have anything that I need to multiply by. But I want a 5x plus 7 on top when what I have is a 13x plus 12. So what I'm going to do here is I'm going to ignore that 13x plus 12, and I'm just going to do plus 5x plus 7. And then I'm over here, I'm going to do minus 5x minus 7. So what I'll end up with, so notice I'm only doing the multiplication on the first part. Everything else is addition or subtraction. So then I'll end up with 4x squared plus 5x plus 7 over 4x squared plus 5x plus 7 plus 13x plus 12 minus 5x minus 7. And I can combine my like terms there. So I have 4x squared plus 5x plus 7. So then I'm going to end up with 13x minus 5x is 8x. So I'll have 1 plus 8x. And then 12 minus 7 is plus 5. So I have 8x plus 5 over 4x squared plus 5x plus 7 dx. x. And now both of these integrals are actually also really straightforward. Don't just immediately go to completing the square in the second one. Notice that the derivative of the denominator is equal to the numerator. So that one right there, I can easily do. I can say this is x plus 8x plus 5 over 4x squared plus 5x plus 7. And then I'm doing like a mini u substitution here. U equals 4x squared plus 5x plus 7. And then du is equal to 8x plus 5. Look how nicely that worked out. So I end up with the integral of 1 over u du, which is just ln of u plus a constant. So this is x plus ln of 4x squared plus 5x plus 7 plus c. Okay, so that is my special division that can be easily used anytime the degree of the numerator is equal to the degree of the denominator. If, however, the degree of the numerator is greater than the degree of the denominator, in this case, we need to do polynomial long division. And I'm just going to do one example of this because in the next topic, we're going to do it a few times. And also in theory, you guys have learned this before. So polynomial long division when the degree of the numerator is greater than the degree of the denominator. Okay, so in this case, the degree of x cubed minus 36x plus 3, that degree is equal to 3. And on the bottom, the degree is equal to 1. And so that tells me that I need to divide because 3 is bigger than 1. And I can't do my special division because the degrees aren't equal. So we're going to set up our long division. If you went to French school, you maybe saw this done a little bit differently. I'm happy letting you guys do it either way. I'm just going to do it once right here in the English way. It's usually pretty mixed in classes as to who did what. So I pick one way and go with it. So here we're doing x plus 6 is going to be divided in to x cubed minus 36x plus 3. And so first, I'm saying x cubed, x cubed on the inside, I'm going to divide it by my x on the outside. So x cubed divided by x is x squared. Then I multiply that x squared down to get x cubed plus 6x squared that I'm subtracting here. Now notice in the numerator in that x cubed minus 36x plus 3, there is no x squared term. So it's almost as if I'm doing plus 0x squared. So I'm actually going to erase this real quick. It's kind of like I have plus 0x squared minus 36x plus 3. You don't have to write that, but knowing it's there might help you with the subtraction. So then I'm doing 0 minus 6x squared. So I have minus 6x squared minus 36x plus 3. And I don't stop there. I keep going. I keep going until I have a remainder with a degree that is less than the original denominator. So here my degree is 2 in negative 6x squared minus 36x plus 3. And x plus 6, it's 1. So I definitely want to keep going. So now I'm going to do minus 6x squared divided by x. And that's going to get me minus 6x that I multiply down, minus 6x squared minus 36x that I'm then subtracting. And notice both of those disappear and I have a remainder here of 3. So this right here is my remainder. And this right here is my answer. And we stop because the remainder has a degree that is less than that of the original denominator. Than that of the original denominator. And that's important because sometimes you're going to stop when there's still an x left over. Sometimes you might even stop when there's still an x squared left over. You stop when that degree becomes less. And now I can rewrite this integral as the answer. So that's x squared minus 6x plus the remainder over the original denominator. So then I do my division, I get 1/3 x cubed minus 3x squared plus 3 ln of x plus 6. All of those were known forms, so I could just immediately integrate. All right, that's polynomial division. Hopefully you guys have a vague memory of that. I'll see you in the next video.